All right, guys. So you can see that it is quite tedious, but it is rather straightforward. So you just need to be calm and know what you are doing, substitute things, write them down as they appear. Then after you completed that task, the technical task, after that just massage them so they will look nice. So what I did while you were on the break, I just took took this equation and rearranged it slightly so it is looks a little bit similar. Okay. So this is something, unfortunately, you will have to do. So obviously, I will be mindful of time. This takes time, and obviously, I will not ask you to do anything as lengthy as that or for your tests. I just need to see sequences. But let us persevere, and let's just write down the equation which comes with from the second match condition, and see what we can do with that. Okay. So this is the equation that appears in the first, comes from the first matching condition, and that appears in its natural form. That's how it looks. And this is the form which we can obtain by simply rearranging that. Okay, nothing special here. Now, just test the concept. So the second one is this condition. So we will need to take this function and evaluate it above and below. That is, of course, much, much simpler. Okay? So tell me what the matching condition in this case is. Remember, so I suggest you always write it in left-hand side is equal to right-hand side rather than difference is equal to 0, including just E here. Okay? So similar to what we've done here. So left-hand side is equal to the right-hand side. And then after that, you just massage it and you get some difficult effects. Okay? So what I would like you to do is to now write similar equations coming from this condition. It will be much simpler, but I'd rather you to do that rather than copying what I have. Thanks.
Yeah, that's it.
Stop. Good. Is anyone ready? So what happens with this? So what? How will it look now? So that's the first matching condition. So the second matching condition. How will it look? So we need to evaluate this from the top. So what happens there? So what is it equal to on the top, above? So this one is going to be E minus capital A e to the power minus alpha minus
b e to the power minus alpha minus c is equal to capital C for alpha equals to 0, right? All right, so this is not the straightforward way of writing that, so I'm sorry. So you will get confused if you do that. So does anyone have a better idea? So what I say, well, you do it by evaluating this on the left or on the top and making it equal to the same value at the bottom. So once again, what this means, so if you still don't understand what I mean by this expression, that means the following. It is psi hat divided by u minus c evaluated at z0 plus 0 minus psi hat u bar minus c evaluated at z minus 0. And that is equal to 0. So that's what this literally means. Is that clear? But what I'm suggesting is not writing it like that, but writing it like that. That's the equivalent form. So what you have on the left is completely upper layer. What you have on the right is completely bottom layer. And they are equal to each other. Is that clear? So that is much clearer way. So for you it will be easier to write it. So therefore, because of that, I would not recommend writing it as this equation from the very beginning. I would like to write something is equal to something. It will be just much more straightforward for you to do that. Okay, so therefore, if you do that, you will get. So can you tell me what you get as if you do that? So you need to do that, right? So you need to evaluate that. So what is psi on the top? A to the power minus alpha z, but z is equal to 1. So therefore, you will get A e to the power minus alpha divided by 1 minus c. And that is to be equal to, so in the second layer, it is b multiplied by e to the power minus alpha plus c to the power divided by z minus c, but z is equal to 1. So that's what I mean. So do it exactly as it appears first, and of course then you see that this can be cancelled, and the rest can be rearranged the way you like it. So clearly here you will get, for example, a minus b multiplied e to the power minus alpha is equal to c e to the power alpha. Right? So that's simplification. So then you will have to, you can also rewrite it further, you can manipulate it further. So, and this will be 2 alpha. Okay, so what I'm saying that the first equation should be written in the form as it is given, as appears. And after that, if necessary, if it is straightforward, keep manipulating that. But after that, not immediately. Write it like that, left-hand side, right-hand side. And after that, start rearranging that. Okay. So what I would like to do next is to write down what you can do from these two equations. So you have A, B, and C appearing here, but only two equations. So therefore, you can make A and B subject of these equations, but keep C as a free parameter, right? And I will not ask you to do that, just we need to make sure that we are on time. There are other things for us to do. So I will simply write what you will get as a result of these manipulations. You will get that B is equal to minus capital C e to the power 2 alpha 1 minus 2 alpha multiplied by 1 plus small c. Sorry, minus. So that's what the expression for B is going to look like. And the expression for A is going to be a little bit simpler. 2 capital C e to the power 2 alpha 1 minus c. So that's what you will get out of two conditions, two conditions if you go through the algebra. Okay? So I do suggest you actually go through the algebra and get these results, but you will do it later on when you are not pressured by time, and just get comfortable with the idea, get comfortable with the type of manipulations that will be required. Okay? So it's tedious, but it is straightforward. So, just to accelerate, I will give you the answers for the second part. And I will ask you, so it will be onus will be on you, so it will be your responsibility to actually go through the algebra and get those answers on your own as a preparation, right? So before the test, go through that algebra, get the result which I show you, make sure that you understand where it comes from, okay? But I will give you the answer. If you do the same thing with the second matching condition at z0 equals to -1, then after some struggle, not much struggle, but about 2 lines of struggling there, you should get the following. You will get C is equal to 2 alpha 1 plus C minus 1 divided by 2 alpha 1 plus C multiplied by D. So we have 4 quantities, A, B, C, and D. And B will be D times e to the power minus 2 alpha divided by 2 alpha 1 plus C. Okay? So that's what you will get from the second pair of equations. Again, you will see that if you write them, you will see that in those equations you will get B, C, and D, and you can only resolve 2 of those because there are only 2 equations. And you resolve it for B and C and keep D as a free parameter. So here C is a free parameter, but C will become defined from the second pair of equations. And then D will remain a free parameter. That's how it works. And this is an important note. See what happens. So in here, we don't really get the solution. We had 4 equations and we hope to determine A, B, C, and D. But it turns out that we only can determine A, B, and C, but not D. D appears to be, will appear as a free parameter. That's unusual. We thought that we had 4 equations, and we thought that we had 4 unknowns, so we thought that everything will be fine. But reality is not that. And what do you think the problem is? So did we really have only 4 unknowns? Just look at this. What do you know and what you don't know? So obviously you don't know D, so you need to define D, so that's one unknown. What else do we know? And what else do we not know here? So we stated that, well, we assume that alpha is known, right? So all right, we will take it as a parameter that we know. So D, we assume that we somehow specify it. Well, we assume that alpha is also known. Is there anything else which we don't really know? Like if we would like to find the numerical values. Small c. So it turns out that in reality, we thought that we have 4 equations and 4 unknowns, but we have more unknowns because c is unknown as well. Right? And that shows. So that's why we get this situation here. So a situation when, well, we still don't have enough equations to define the whole thing. This is very typical of stability studies. And this will come in various reincarnations, but that is the basic idea. So you will never have enough equations to solve the full problem. So you'll have to do something else. All right, but in this particular example, we can take the following path. Look, we have this equation, and we have this equation, both defining the same quantity. So therefore, if I take right-hand side of this equation and right-hand side of this equation, they must be the same, right? So therefore, I can say that this is equal to that. Agree? Agree. So, but this contains constant c, and c itself contains d. See the chain here? So if I take this and equate it to that, it means that somewhere I will have to stick this in. Okay? And let me do exactly that. If I do that, I will get e to the power minus 2 alpha divided by 2 alpha 1 plus c is equal to 1 divided by 2 alpha 1 plus c minus 1 multiplied by e to the power 2 alpha 1 minus 2 alpha 1 minus c. So that's what I will get. Now, can you see where it comes from? So what do I have on the left-hand side here? It's just this without d, right? Okay. What do I have here in brackets here? So that is just an expression for c, right? So which one though? So this one, 1 minus 2 alpha, that's this one, right? So all this is just copy and paste. But this is equation for c, which is, so what I've done here, I simply divided through. So it's not a fraction, so I divided through, so that will become as 1, and this will become 1 divided by that. Agree? All right, and where did d go? Because d multiplies left-hand side, and d multiplies the right-hand side, so it cancels, right? And I can only cancel it if d is not equal to 0, right? So if d is equal to 0, you cannot divide by it. But can it be equal to 0? Can d be equal to 0? What will happen if I set d equals 0? So if d is equal to 0, then b is equal to 0. If d is equal to 0, c is equal to 0. If c is equal to 0, then a is equal to 0. Everything dies. Nothing left. So No, we cannot afford that. We'll lose the whole thing. Okay, so now that's the condition that we have, and it contains absolutely no constants, no A, no B, no C, so they all disappeared, they were eliminated. But it contains still constant C. So therefore, it is clear that this equation is not for A, B, C, and D, it is equation for this little c. And if we resolve this, again, I will skip the algebra. I will simply state that C is equal to 1, not plus minus, two alpha squared minus E minus 4 alpha press the wrong button, so what do just this one, yeah. Minus 4 alpha divided by 4 alpha squared, and what I will do, rather than taking square root, I will write it as c squared. So that's what you will get. If you resolve this, that's what you will get. So obviously what you will get is quadratic equation, so it takes a little bit of time to manipulate that, but that's the final result. All right. Now, do you remember what C is? It is I sigma divided by alpha. So therefore this will be minus, so I squared gives you minus 1, sigma divided by alpha, right? Squared. Agree? All right. So therefore I can find sigma out of there. So, and if I do that, I will get sigma squared is equal to minus alpha squared c squared, which is equal to e to the power minus 4 alpha minus 1 minus 2 alpha squared divided by 4. So that's what the expression is. And if I want sigma itself, I just put the square root here. And this will be 2. Well, clearly plus or minus. Agree? Okay. So, if you look at this expression, it contains square root. If you have square root, you have to be mindful of expression under square root being negative. If it is negative, what happens? What's this, the value of sigma then? It becomes imaginary, right? So remember what the meaning of sigma is. Sigma is sigma r plus sigma I, so it contains growth rate and frequency of oscillations. So if this becomes negative, then sigma becomes purely imaginary. It does not grow because sigma, a real part of sigma is 0. So it does not grow, it does not decay, but it does oscillate. So therefore, what we will be able to see is some sort of oscillations. which might or might not grow, so they will, they will not grow, and therefore their amplitudes, because remember that what we are trying to do here is to assume that the amplitude is very, very small. So therefore, overall, if the amplitude of these oscillations is very small, will you be able to see any of them in physical reality? No, right? So yes, they are there, but we cannot see them. They're too small. So they have to start growing for us to be able to see them. So therefore, we need to insist on the fact that this is positive, right? This expression under the square root is positive. But if it is positive, then square root of a positive quantity is real, purely real. So therefore, it is not going to oscillate. It will just be growing. But we will have plus and minus. So we will have also decaying. But we will see also growing. So therefore, decaying and growing, some of them will be growing, some of them will be decaying. So therefore, the perturbations will consist of two classes. Some of them will die, some of them will grow. Clearly here, we don't care about those ones who die, right? So we do not see them, so they will just disappear. Even if they are there, they will disappear. But the ones which are there to grow, that's what is of interest. Is that clear? So therefore, we are interested in the case when sigma r is equal to e to the power minus 4 alpha minus 1 minus 2 alpha squared square root of that divided by 2, taken with plus sign. Okay? So that's what sigma is, and from here, of course, you will be able to find what c is. Now, this is quite a complicated function. It is not trivial, right? So we need to plot it to see it. And that's what I will do next. So I will show you, run a MATLAB code which produces actually a graph of this function. I'm sorry, I'm losing my... I'll just put it in my pocket. So, let me just start the code here, and then I will display what the output is. Okay, here we go. So, this is a MATLAB code that you will find in the directory along with the rest of the files, and you, if you wish, you can play with it. So, if I run it, the first thing you will see is this. That is the plot of that function, sigma function. You can see how it behaves. So it becomes positive. It does have positive values. That's the positive values are here. But those positive values can only be observed up to a certain point for a certain range of alpha. So along the x-axis, it's alpha. So that means that what we will see only is a set of waves with certain periodicity parameter. So alpha is a periodicity parameter. So the larger the alpha is, what happens to the wave? If you have a sinusoidal wave with one alpha and the second alpha is smaller. So this is alpha 1 and alpha 2 is smaller than alpha 1. How will it be? So what will happen with the period? Large. So it is inversely proportional. So the smaller value of alpha you have, the longer period you have, right? So if alpha is equal to 1, you will get something like that. If alpha is equal to 0.5, 1/2, then alpha, the wave is like that, much wider. Okay, so therefore, if alpha becomes large, the wave becomes shorter. And if the wave becomes too short, too compact, so too oscillatory, it cannot exist. And that makes sense. The reason is that if it becomes short, right, it oscillates too quickly, And any oscillations require energy. Right? So not enough energy, so there is a cutoff. And that's what we see here. But the important thing is that the instability, so those waves, can be observed for various values of alpha, not for a single value of alpha, but for the whole range. And the question is, which one will be selected? So if I have a choice of all these, obviously it is infinite numbers, so even though the range is limited, so the number of modes which contribute to these oscillations is infinite, right? So infinite number of points here. So which one of them will be observable? What do you think? Remember how it works. So we start with low noise. And that noise starts growing. And that noise consists of all these components taken together. And what we see here, that they are all there, but they grow differently. Okay? So which one do you think you will be able to see sometime later? Because they all start from the same base, low base level, low noise level, and they start growing, but they grow differently. So what will you see at the end? So which one?
Watching logic. Cannot English, so alpha for values of alpha, the value of sigma is positive. We need to a relationship of sigma to the largest,
Right? Because this is the value of alpha for which sigma is largest. So that means that the growth rate is the fastest. So therefore, if you wait the same time for every single of these modes to grow, this will be just overgrowing everything else. And once it becomes large, you cannot really see anything else. Right? So that's just tall poppy syndrome. So if one goes up, so it dominates the whole thing. So therefore, what we see here is an example of typical linear stability problem computations. So our goal is to define the growth rate, not those constants, but the growth rate. And then see whether that growth rate changes with wave number. And frequently it does, as what we observe here. And then the question is, what do we actually see in reality? And in reality, what we will see, not any of these, but only the one which grows fastest. Eventually it will dominate, right? Everything else will be dominated by this single mode. Okay, so therefore the problem then reduces to a question, at which wave number perturbations or disturbances will grow the fastest? That's the typical question that we need to answer. And again, this is absolutely generic. It does not really matter whether it is a fluid problem, whether it is viscous, inviscid, or any other problem, whether it is elasticity problem, whether it's solid mechanics problem, anything. Well, eventually it all boils down to growth rate and the wave number at which that growth rate becomes largest. Absolutely general idea. Algebra behind that is tedious. Algebra behind that is specific to the chosen problem. The question, fundamental question, is exactly the same. Okay? So, now, I promise you to show that this is actually physically relevant. So this simple problem actually is physically relevant problem. And to do that, I'll just refer, first of all, I will show you some pictures. Further pictures. Okay, where is it? So this structure of the code, it just pauses, and if you click any button, it will produce the next picture. And guess what I have here? So what I have here is actually the plot of the solution. That's stream function psi. Okay, we found it. We found those coefficients A, B, C, D, and I found the value of alpha at which the growth rate is largest. Okay, just by looking at the code, so it is all inside the code. I don't do it by hand, I do it numerically. And then I pick that particular value of alpha. I compute particular values of coefficients A, B, C, and D, except D is arbitrary. D is arbitrary, so therefore I just set D equals to 1, for example, or some value of D, right? And I set that component, that coefficient D to a particular value of my choice. I don't know what it is, I just choose something. And I compute the rest. And then I know that the solution is actually not psi hat, but psi hat multiplied by e to the power alpha x. And then e to the power alpha x is essentially e to the power e multiplied by cosine of alpha x plus I sine of alpha x. So therefore, I need to add complex conjugate or real part. And that's what I plot. Obviously, I cannot plot complex valued functions. And that's what I plot. And that's what the field plot looks like. Look at these cells. These are stream function cells, and sorry, these cells here. So, and you can see that there is a discontinuity bit of the slope because we are changing the region. So, because the base flow is different. So, on the top, the flow is to the right. At the bottom, the flow is to the left. And in the middle, it's just a joining line, mixing layer. Remember how the original plot looks like? Velocity, so to the right on the top, to the left at the bottom, and straight line profile in the middle. So therefore, whatever happens here will be carried to the right. Whatever happens here will be carried to the left. And as this happens, you will have a shear. And if there is any sort of perturbation which occurs in between these layers, shearing layers, so say this is perturbation, and it is in between, sandwiched in between the lower level, which will go that way, and the upper layer, which will go that way. What will happen to it? It rolls. It rolls, and that's what you see here. So if I add these perturbations and the base flow, which is just a shearing flow, you'll get that. And that's what you see. Okay, that's good, but does it have anything to do with reality? And historically, that was actually observed. So so-called, what we're dealing here is so-called Kelvin-Helmholtz instability, which is the first observations of that that led to this research. Were quite a long time ago. I don't exactly remember when, but it was before Rayleigh. It was before Rayleigh made his famous, invented his famous equation. So before that, so they observed that. And does anyone know where they observed that? No? Don't know the history? Never heard? It is a weather phenomenon. So in the sky, you have a layer of clouds, and wind blows along, if we have the clouds positioned at the right height, so there is a shearing flow. So jet stream, for example, in upper layer of atmosphere goes in one direction, but in local wind goes in the opposite direction. So you have these two winds meeting, but one wind is at the bottom, has at the bottom layer of the layer has one direction, and at the top layer, jet stream, for example, will have a different direction, completely different direction. So we have a shearing flow, and if it happens that clouds are stuck in the middle, then we will see what happens to those clouds. And that leads me to another demonstration which I would like to show you. And so that's just a repetition of the same pictures in your lecture notes. And that's what you see. That's a real picture. Obviously, it is not from the... Just want to make it bigger. You can see these phenomena. So, and I saw one last year, so about November last year in Melbourne. So what you see here that the top wind is from left to right. At the bottom, the wind is from right to left. And clouds are here. So you have this vortex. And that vortex takes the cloud from the bottom and pushes it up. And there, the flow catches it and pushes it to the right. So therefore, you have a circulation like that. And that's how it looks. Okay, so you do not see anything here because the cloud has to travel all the way there to complete the circle. But unfortunately, clouds will eventually evaporate. Okay, so therefore that takes quite a long time to get there, so therefore they evaporate on the way and you cannot see that. That's why that's weird shape. Okay, so that's how it works. So how are we doing with time? We finished? It's okay? 15? Mm-hmm. All right, so that is the idea. So the concepts or conclusions that we made here are, so linear stability analysis, which we just considered here, so which ignores nonlinear terms, cannot define at least one of the coefficients, like in our case D. Coefficient D remained as a parameter. But it does define the growth rate, and that growth rate is not a constant. It is a function of wave number alpha. The wave number alpha at which the maximum growth rate occurs frequently is referred to as a critical wave number, because this is what we will see first. We will see in experiments, we will see these patterns which correspond to the wave number with the maximum growth rate. So algebraic details of how growth rate is to be computed very much depend on the type of the problems, but we will see that in further studies, in further lectures later today, that this can be formalized. And that will be much easier to see on the next example that I will consider, which will be essentially a viscous flow application, Poiseuille flow, channel flow. And it will be best to be seen not in terms of streamlines, stream function, but in terms of variables u, v, w, so-called primitive variables. So I must say that whatever we've done here, we introduced all these stream functions and so on and so forth. So this is quite important from a historical point of view, because people simply had to rely on their brain and algebraic skills to deal with these problems like 100 years ago, or 50, even 50 years ago. Nowadays, computers are much, much stronger, and we can solve a larger variety of problems using computational power. But we need to formulate the problems in a way that are not focused on our algebraic abilities, but rather on the ease of computational implementation, because computers have different minds to us, right? And they follow different rules, so therefore we need to be mindful of that. And the rest of this subject will be devoted to modern applications of theory and modern formulations of the problem. And most of them will be taking advantage of primitive variables, which in a sense are more natural, because you start with Euler equations, for example, and you do not modify them, you do not introduce anything else, you just stick with them. Okay? So that's what will happen. Now, the rest of this lecture, I would like to use that time, so about 10 minutes, right? 10 minutes. So to guide you through introduction to viscous flows. So what I would like to do is to refer you to my lecture notes, which very briefly, very unrigorously introduce so-called Navier-Stokes equations, the equations that describe motion of realistic viscous fluid. So rigorous derivation of Navier-Stokes equations is quite involved and requires a lot of mathematical knowledge, special mathematical knowledge, for example, tensor analysis, Don't have time for that, and I don't want to dive into that. What I usually do with my undergraduate students, I give very much qualitative introduction to Navier-Stokes equations, physically based. And this is what I have in my lecture notes. Several pages of my handwritten lecture notes, which will be available in the for download from the website from the folder. I will put them in tomorrow, by tomorrow. So after we finish today, I will put them in. And please read through that. But I will not have time to discuss every single detail of them. I will just glide through them now. And after the break, in the last hour, we will be dealing with solving those, not introducing those. So that's what I will do next. And I will not write much on the board, but what I will do, I will simply comment on what I have in my handwritten notes. So these are just very qualitative statements that I will make. The rest you will be able to read. So first of all, viscous fluid and viscid fluid. I already mentioned, in viscid fluid, layers slide. They do not touch each other, they don't know about each other. That's the situation here. Two layers of fluid particles, one goes over another and they do not bump into each other. Now imagine that they are closer together. And if you try to pull this chain of balls against each other, they will start colliding. And if they collide, then they will feel the presence of each other. So they will start communicating with each other. Right? If they communicate with each other, so by exchanging momentum, so they hit each other. So imagine that these are billiard balls. What will happen if this ball will hit this ball? Which way will they move after collision? Will they stay in the same line? No. So this is the very basic and very important distinction between the viscous flows and inviscid flows. In viscous flows, in order to move this layer, you have to pull it in the plane of the layer. So if this is to be moved, you have to push it that way. And that's the only way you can move it. Here, you can move the top layer, apply the force in this direction, horizontal. But it will push the lower level down as they include. So as they communicate with each other, right? It's like you going through the crowded place, right? You go straight, but if somebody is on your way and you bump into it, so that person goes sideways, right? So the force applied in one direction causes the reaction in the other, completely other direction. So that's the difficulty with describing flows of viscous fluids. That's what happens. You apply the pressure in this direction, but the fluid starts going in the other direction, in a different direction. So that's this. The other thing is that we started talking about interaction between layers, and this happens through the surface of layers. So therefore, we need to introduce the concept of the force acting on a surface. But that means that not only we need to derive the expression for the force itself, but we also need to describe the surface on which it acts. And the force may be the same force, but the surfaces could be all sorts of surfaces. So, therefore, the introduction of into viscous flow equations requires introduction of the so-called stress, concept of stress. Stress is a force acting on a unit area of the surface. It is similar to pressure. The only difference is between stress and pressure is that pressure is always acts perpendicular to the surface. Pressure cannot act alone. Friction force can act alone. And friction force can create tangential stress. So friction force applied to a surface area will be distributed over that area, and each unit element of that area will feel this stress. Okay? So therefore, we will have two stresses, two types of stresses. One is tangential, which acts in the plane of the surface, and the other one is normal. The normal one is created by pressure, because pressure acts to press it down. Tangential stress will come primarily through the friction, through viscosity. Okay? That's what will happen. So this is what I describe here. And then you need to introduce a specific mathematical description for those stresses. And that's what I have here. So this is just a sketch. We will need to go through that on your own. So basically, it introduces these stresses, and they are tensor elements. They have two indices. And the convention is that the first index shows you the direction of the force. In this case, for example, I chose indexes x1, x2, and x3. So they x1 is our normal x direction, x2 is our y direction, x3 is our z direction. But it is just easier to use these numerical indices to describe a much more complicated situation. So therefore, sigma 2,1, it means that this is the force acting in the second direction, so this vector here, so sigma 2,1. It is the force acting in the direction of y, that way. So the first index is the direction of the force. But the surface to which this force is applied is perpendicular to x1 direction, right? So this triangle OBC has the normal which is in x1 direction. So, and it experienced the shearing force in the y direction. So this triangle is pushed to the left, but to describe the triangle itself, we need to show that it is perpendicular. Its normal is perpendicular to or parallel to x1. So that's what 2,1 means. Okay, force acts in the x2 direction. Normal of the surface to which this force is applied is in x1 direction. So that's what we have here. And then what you will see described here is that balance of forces. So essentially, if we have a fluid element of this shape, if the fluid is less to its at rest, well, it doesn't experience any total force. So therefore, all these stresses must balance each other. Okay? So whatever pushes it to the left must be contracted by whatever pushes it to the right, so that it stays the same. And from here, we will see all sorts of force balance equations that you will see described here. So go through that algebra, and you will see how the individual forces are computed and what that leads to. The next thing is consider another fluid element and just consider the shear. So if there is a shear, some sort, it will start rotating. We saw those vortices, right? That's what will happen when we have shear. But if we do not have any sort of shearing forces, so if viscous fluid is just left alone, obviously there will be no rotation. And that leads us to another consideration of a relationship between these forces, because if there is a disbalance of forces, then we will start experiencing rotation, right? So that's what will happen if there is shear. So therefore, the rotation under normal condition, if there is no forcing, there is no rotation there. So therefore, that's another bit of information which we have here. So what happens because of that? And then there is a model. So we need to describe the shear stress, right? So how quickly one layer slides with respect to another. And once this is done, we need to relate it to the force produced by that shearing, so friction. Okay? So in solid mechanics, the friction force is proportional to the pressure force. So you push hard against the wall, perpendicular to the wall, and this increases. The friction force increases. Experiments show that in fluids, the dynamics is completely different. It's not pressure-based. It is based how quickly one layer slides with respect to another. So amount of stress, if a motion is like that, is different to quick motion. right? So that's what happens, and you know that. So if you have cold hands, try to do that. Nothing. You do not feel anything, but try that, and you will feel the heat. So friction starts working. So therefore, the model needs to be introduced to relate the strength of shear with the actual force, friction force experienced. And the simplest model and the most universal model is Newtonian fluid. Newtonian model states that the shear, shear rate, so how quickly one layer slides with respect to another, is directly proportional to the strength or to the friction force it produces. And the coefficient of proportionality is viscosity coefficient. And that is introduced here. So this coefficient is not mathematically computable quantity. It is the quantity which needs to be defined experimentally for each individual fluid. So it is experimental fluid. So therefore, after all this, we end up with equation which looks like that. So what we have here is exactly as we had before. This is just Euler's equation. And this is the pressure gradient term, exactly the same as before. And this is the gravity term, so you might or might not have it. You might absorb it in there, but I kept it here just for the sake of it. But what is important that we will have an additional term, which is called viscous dissipation. This is due to friction. Mathematical details of how it is obtained, why it is written in this form, that's part of the discussion in these lecture notes. Please go through that. Many of you have seen that before. If you studied fluid mechanics before, you will know that already. So I'm not going to focus on that. And that is the system of equations that we will be working with from now on to the end of this subject, which will describe realistic fluid with viscosity. We will still consider incompressible version of fluids, so to make our life easier. But that's basically all I wanted to tell you about viscous fluids and where to get extra information. So what I will do, I will put these lecture notes online right now, and if you have a time over the break, look through these few pages. Don't go any further than that before the start of our next lecture. What is it, 4 o'clock? Before 4 o'clock. Okay, so I'll put it in a group folder now, and once it is there, access it. Once you have your lunch, go through that, and I'm happy to stay after the formal class. And if you have any questions about that material, I would be available to discuss it with you individually after that, if necessary. Okay, but I will not be going through that in detail. So just read it on your own. Okay, done for today.